Yes, so this last session is going to be more abstract. We're going to talk about general ideas. And the idea is that most of the time we have a sample of data. It's either a sample of a data set, data points, or it's a sample of a distribution coming from MCMC or sampler. And what we want to do is compress this information to transmit this information to other people. And we're going to talk a little bit about the different levels of compression that you can put in your paper. You want to print it, so you have to have information that can be transmitted either by text or by images. So one of the first steps we all usually do is try to compress the whole distribution into some of its statistics. And one of the first one we want to always do is have an approximation of what the probability density function is. So we all use either histograms or other methods, for example, kernel density estimation, which give the same information, which is an approximation of the probability distribution function. Of course, it's easy when it's one-dimensional data. When it's you have increasing dimensions, what we do is some of you showed some result. We do some triangle plots, which is try to get projections either marginalized on one dimension or marginalized on 2 dimensions, because we cannot print into 3 dimensions. But if we could imagine and see a 3 dimension more easily, we could even have other information here on a higher dimension. And we also go to extreme compression, where we summarize the whole distribution by a point estimate, which is a central value and an associated what we call uncertainty. If we have centrally peaked and not too asymmetric, we tend to use a mean per standard deviation. If we don't have this ability to approximate, we go with a median with some interpercentile range that we often choose to be 16% and 84% to match this definition in the case of a Gaussian distribution. And we give this data, and we typically print it in tables. And for higher dimension, we can, having a few, if we get this hypothesis that we're in a Gaussian regime, we can summarize the uncertainty into covariance matrix to have all the information about the different correlations between the data that we show. So this is how we quote errors. We also have ways of plotting the errors. So the errors associated to a measurement. Most of the time, we use error bars. Okay, this is just a graphical representation of this point estimate. Sometimes we go to asymmetric error bars in this case, but there are some other ways of showing this information that sometimes can be used, sometimes becomes too much information. It's not synthesized enough, but still there are some things that are called violin plots, where actually what you show is a little histogram, tiny histogram or tiny kernel density estimation around each one of your points to show more information than a simple point estimate. And also sometimes you don't have a sample of points. Sometimes, for example, you have in your code base, you have a black box optimizer that gives you a number, tells you, okay, I've done a maximum likelihood or chi-square minimization, and this is your best value. And sometimes they don't give uncertainties. And if they do, usually they are computed by adjusting a local curvature around this maximum likelihood or minimum chi-square typically, and they assume Gaussian error, and actually what they output is a covariance matrix, so you can have it. And if the method doesn't give you any uncertainties, you still can try to use bootstrapping. So Frederick talked a little bit about it, and this is a different variant of bootstrapping in the sense that you only have one data set, and from that data set you can get one value. And you will create many, okay, 10,000 or even more, new data set by sampling with replacement from this unique data set that you have. And then you compute the value that you want to have from each of these resampled data sets. And you're back to the same questions that we had before. You now have a sample of points that you can describe by every information that, that I've shown before. So this is the first part about plotting and quoting. Afterwards, we can talk about transmitting. So if you have any comments, it's all about compression. We get from a full data set to information that we can transmit. At each stage of the compression, we lose information. And the compromise is which is the best way to show in our plots and papers, because this is the way we transmit information, the main way. Well, the idea behind bootstrapping is really that you have a data set from which you can compute certain quantities. It doesn't work for all parameters. It works when you have a large data set and you from the output you get one value. And what you do is you slightly modify your original data set by allowing you resample your data set to create a new fake data set, and you do it a lot of times. It's a bit of a magic. Bootstrapping is a bit of magic. I don't know what we're losing when we're doing it, because I'm not a specialist of bootstrapping, but it works sometimes. It doesn't work all the times. No? Okay. Sure. You can keep the microphone, John. And one for François too.
I'm not sure it's answered two questions, but I'm not sure that it's well, because you are saying that each time you compress one quality or you will lose information. My idea is that each time you will compress your information, you will extract information.
What I mean,
that's a different. All the goals of what we are doing is to try to understand it, and so to extract information from that. And that's the question: how do we ensure that what we possibly do for information and not?
What I mean, for example, is when I show this, if I show this representation here, there are other distributions than this one that have these same point estimates, this same median and this same one percentile here and one percentile here. I could have other realization of the distribution that get the same information. This is why I'm saying there's a loss of information. Unless, for example, I tell you what distribution, what family of distribution it is. Then I've given you more information and you can reconstruct completely. What is? Well, yeah.
The goal is not the goal is to make sense of your data, so you don't want to transmit everything.
No, but for example, if I want to do a Bayesian approach where I want to use as a prior the distribution of a previous set of experiment. There's one of my input parameters for my model is one of your output parameters of one of your model. If you just give me a point estimate, I have to make a hypothesis on what is the family of the distribution and then sample from it. If you give me the full distribution, I can directly, the more information you give me about your samples, the more information I can use and more correct information without distorting what you meant to give me. The next part is about that, about what we transmit and how we transmit it. Yes. Well, yes.
It's all about the research and science, and so you want to be able to compare to other things, and you need as much information as you can in order to apply information.
And maybe you have different ways of transmitting information. We have the paper, but we can also have ancillary data. We have other ways of transferring information than just the paper. So yes, this is about the next part, transmitting this information. So the first question is what to send, and then we'll ask how to send it. So in decreasing orders of compression, you could send the samples themselves. You can send the data set. You don't have to just send the average value and things like that. Of course, and this depends on, can be huge, can be not transmissible, but you could send the samples themselves and then tell the next person, well, redo the job that I've done and get the values you want yourself. You could choose a family of analytic distribution and then compute the associated parameters. Basically, you fit your distribution with a family, and I give you the family and its parameters. And from that, you can reconstruct any samples you want of the distribution. You could send the parametric description, you send the histogram of the KDE. You could send the point estimates, possibly with the covariance matrix. And this is typically what we do in our papers. We print tables of point estimates, and that's it. For Bayesian difference, you could send the data set and the likelihood, or the data set and the forward model, and let someone resample as many more points as they want. So kind of reproducible science. You can redo what I've done just by having the data set and the way I've treated the method. It would be interesting to see if different sample methods give the same results. We have also sampling errors. And how to send it? Okay, so this is even more technical. By increasing level of difficulty, you could send a table in your manuscript. You could have a new, a more digital version of your table in an ASCII table of the same point estimates. You could use some structured format, like for example JSON, pandas, or pickle if you want to send a bit more information, but you have to be careful of strange formats because they don't live forever. There's a strong survivor bias. So we remember the formats that have survived until now, but we forget all the ones that have never survived. And there are many more that have not survived than the ones that survive until now. So this can be dangerous for long term. For larger data set, of course, we have binary formats already, and we have fits, but there are other ones that are used, ones that have different kind of structures depending on the type of data you have. And some formats are trying to become standard for the samples from the distribution. For example, RVs has a structure that's called inference data that is trying to standardize the way we transfer outputs of samplers for the MCMCs and approaches. And maybe one day, maybe one day, because of reproducible science, the editors will ask us for the Python scripts or scripts that create all the figures and the tables in our paper from the data. Some editors already asked us for the data set, and it was not the case a few tens of years ago. And maybe one day we will have to create the scripts and transfer all the information chain from the data set to the published data. And in that case, well, from that script, you will be able to extract all the information about the uncertainty. So that's it for me.